All right, good morning, everybody. Let's get started. Let's start by showing by a show of hands if you can hear me. Okay, perfect. Thanks, Stephen and Caesar for letting me know. Tony, thank you all for letting me know. First things first, there's a midterm coming up tomorrow, and that includes all the way up to chapter 6, including the material that we covered in the class today. Okay, including MOSFETs and including diodes and semiconductors. Okay, that's about the midterm. A couple of quick things. You want to double check on Moodle. Lab scores have been posted on Moodle, so you really want to double check and make sure your work has been graded. Okay, the TA has been doing an excellent job in keeping up with all the grading work, so thanks to him. You want to quickly double check, and when you have when you notice a discrepancy, if you do, it's not possible, but if you do a rare discrepancy, if at all, send me an email sooner than later, because we only have one more week before the finals week, and you don't want to be stuck in a position where it's too late for you to notice any discrepancy. Okay, that's one thing. The other thing is, after the midterm tomorrow, over the weekend, you want to make sure you get caught up with the labs. If you're lagging with the labs, if you're one lab or two labs behind, that's fine. I don't have a problem with that. But by the beginning of next week, Monday, okay, you want to make sure you finish demoing all the labs up until that date. Okay, by Monday of next week, you want to make sure you're done with all the labs 1 through 5, and you should be ready to demo any areas, any labs that you did not do yet. Okay, because lab 8 is going to take a lot of time, and you don't want to have any pending labs while you're working on lab 8. It's going to take a lot of your time for the design exercise. Okay, so work on the weekend and make sure you're all caught up with the labs. I have been a little flexible with the lab timings. I know the summer semester is extremely busy and it could get hectic, and that's the reason why I'm not imposing these dates too particularly for the labs. Okay, even if you're a day here and there, a week off, that's fine with me as long as you finish the work and learn what you're supposed to learn. Okay, so take advantage of that easy policy in terms of the dates. Okay, and get it done by lab 7. Okay, by Monday, that'll be your last day to work on all the show all the previous labs. After that, okay, on Wednesday, if you want to show any of your labs 1 through 6, it'll be too late. Okay, so you want to make sure that you're taking this lab 7 Monday 22nd, okay, as the deadline for all your previous labs demo. Okay, all right, so let's get started with where we left off. We started talking about channel length modulation. The idea of channel length modulation, it's a higher order effect. Okay, we are very familiar with the equation in saturation for the drain current. ID is 1/2 mu n C oxide W over L VGS minus VTH the whole square. So far, we assumed that the drain current is independent of the drain voltage, okay, in the saturation region. But that's not entirely true. We notice that the increase in drain voltage modulates the channel length, moves the pinch off closer to the source by increasing the drain voltage, and that dependence is incorporated by using a lambda or channel length modulation parameter that multiplies VDS. Okay, this is an enhanced equation for the drain current. Now, ID is the drain current in saturation region. Okay, this is the expression for saturation region. The linear current, the expression for linear current does not change. Okay, what only changes as a result of channel length modulation is the expression for current in saturation region. Okay, so it's a higher order effect. Now let's move on and look at other higher order effects. Any questions, please? Any questions so far before we move on to looking at the higher order effects? And by the way, this is the expression for drain current incorporating the channel length modulation for NMOS, channel length modulation for PMOS. Okay, if you want to find the value for lambda, that can be expressed in terms of early voltage. Yes.
So, like, do we need to learn these equations?
You can use a cheat sheet. I don't care. It's all right if you want to use a cheat sheet. But yes, in the long run, if you want to be comfortable in 109 codes or any other 234 codes, 151 codes, so on and so forth, all of these codes, you'll see this equation so often, so frequently in your life that even if you make an effort to not remember, it'll still stick in your head. All there is 1/2 mobility oxide, the aspect ratio, gate to source voltage, 1 plus lambda VDS. Okay, try not to remember. Okay, that's a challenge to you. So you should really ask me, is there any way for me to forget this equation? Well, unfortunately, there's no way. It's going to stick with you for the foreseeable future. Okay, you'll remember that even if you make an effort not to. All right, let's look at other higher order effects. Other questions, please. Other questions that you want to look at. Okay, so far we started talking about MOSFET, and let me see if I can quickly copy something from earlier page, this guy. Okay, that way I don't end up redrawing all of this. Copy this. But I want to understand the body effect now. Here is the, okay, here is the layout of a MOSFET. Okay, all of that is, okay. Okay, so that's MOSFET for you. Here is the drain, gate, and source terminals, right? Drain, gate, and source terminals. And then there's a current flowing between the drain and source terminals. Okay, now what we want to do is to understand the effect of the fourth terminal. We have been ignoring this guy. What's this terminal? Remember the fourth terminal? We call this the bulk or the body or the substrate. If you remember the construction of the N-channel MOSFET, okay, these were heavily doped N-type regions. This was a heavily doped N-type region, and the substrate itself was lightly doped P substrate. Okay, remember I talked about this when I last talked about the idea of PN junction diodes between the body and the drain, right? And you always wanted to reverse bias these diodes. And that's the reason why you tie the P substrate of N-channel MOSFET all the way down to the most negative power supply. Remember that? So we talked about the body. Okay. So far we have been ignoring the body. When we looked at the MOSFET, we only looked at the three terminals. Okay, I looked at the drain, the source, in the gate. I did not, and I conveniently ignored out of my discussions the fourth terminal, the body. Okay, the fourth terminal. It does have an effect. As a matter of fact, it's called a back gate. Okay, in order to make the idea of body effect clear, body acts as a back gate. Okay, and I'll show you what I mean. We are interested in understanding the body effect. Okay, as you will see, VBS. Okay, the voltage that is applied on the voltage that is applied on the body with respect to the source, that modulates the threshold. So far, if you look at the equation for drain current, there were two equations. ID is mu n C oxide W over L, VGS minus VTH into VDS minus 1/2 VDS squared. This is in the linear region. ID is 1/2 mu n C oxide W over L, VGS minus VTH, the whole squared into 1 plus lambda VDS. This is in saturation region. Okay, the assumption so far has been quietly that this guy VTH is a constant. Okay, earlier in the problem in the last class, I mentioned VTH was 0.5 volts and that it was not going to change in the previous class. Okay, VTH. What is VTH at all? Okay, so changing VTH, by the way, if this were not constant and if this were to change up and down, what do you think happens to ID? Okay, I'm going to show you, simplify this and show you only one equation, the equation for drain current in saturation region. Let me write it out, VGS minus VTH, the whole squared. Okay, assuming everything else is constant. Okay, assuming everything else is constant, what do you think happens to ID if VTH were to change? If VTH increases, what happens to ID?
It decreases.
It decreases, thank you, because it's in the negative term, right? VTH is
Yes.
subtracting the term, okay? So if VTH were to go down, correspondingly, there's going to be an increase in the drain current. So there is some dependence for ID on the threshold voltage, okay? It's an important parameter. As long as this is constant, it did not affect, ID was not changed by VTH. But if VTH itself was not a constant, but dependent on some terms, then ID is going to change in relation to VTH. Okay, the idea of body effect is that VTH is a function, or it's the other way around. V threshold is not constant, but it is a function of the body to source voltage, VBS. Okay, so VTH modulates as VBS, and that's the idea of body effect. In order to understand that, let's look at the operation of MOSFET, the layout of MOSFET. Okay, this guy. So the very operation of MOSFET depends on the fact that let me reduce the pigmentation on this. Okay, that when I apply a positive voltage on the gate, electrons are going to line up underneath the channel. Okay, when I apply enough positive voltage on the gate, so when there is enough positive voltage, or when VG is equals to V threshold or greater, there's going to be a continuous channel of electrons. Okay, by definition, therefore, V threshold is the amount of voltage that you have to apply on the gate. What voltage do you have to apply on the gate to turn the MOSFET on? That is the definition. VG, or the definition of V threshold, is the gate voltage that you have to apply for the MOSFET to turn on. Okay, that's the definition of threshold voltage. Okay, now let's say in a very crude terms, just for you to understand, okay, and this does not pan out to be the exact operation, but it will give you an intuition. Okay, there's going to be slight difference here. I'm going to explain it in very, very informal terms. Okay, just to understand intuitively. What do you think if I apply a positive voltage on the body? What do you think happens? Some of the electrons, instead of lining up underneath the gate, they are now going to go towards the body, right? So some of the electrons are going to go towards the body. So what do you think happens? The MOSFET is suddenly, the channel is not completely formed and the MOSFET is therefore not completely on. So in order to make the MOSFET completely on, in order to turn that guy on, what you would have to do is to apply, to apply more positive voltage on the gate just to turn the MOSFET back on. All right. So in other words, what you're doing is the amount of gate voltage needed to turn the MOSFET on, that goes up. And by definition, that's the threshold voltage. So that goes up. So to summarize, by applying a positive voltage on the body or by increasing the body potential, the threshold voltage is changing. Okay, the threshold voltage VB, by modulating this guy up and down, the threshold voltage is changing. It simply is acting as a back gate. Okay, the relationship that I mentioned is not quite true. As VB goes up, VT goes up. That's not quite true. I'll show you why. But you still get an idea, right? By applying some positive voltage here on the body, it's going to make the formation of the channel that much more difficult. It's going to need higher amount of potential to turn the MOSFET on, and the amount of potential needed to turn the MOSFET on is called the threshold voltage. Therefore, the threshold voltage is being modulated by the VPS. Okay, that's the idea of the body effect. The body has an effect on the threshold voltage. Okay, let's see the expression here. The expression for the body effect is VTH or VT equals to VT naught, the nominal voltage, plus some gamma, the body effect parameter, times 2 phi F plus VSB minus root 2 phi F. Okay, work function. So I welcome you to go back and look at all of these terms, the definitions for VF, phi F, gamma. Gamma is the body effect parameter. We know some of these, C oxide, Q, the doping in the substrate, so on and so forth. Okay, that's N sub is the doping amount in the substrate concentration. So look at this, Ni is the intrinsic charge carrier concentration. So we know all of these terms. The important thing that I want you to understand is more the intuition behind this. Don't get lost with all of these terms. The only thing that you want to understand is the threshold voltage here. The rest is all constant, is a function of VSB. Okay, if VSB is 0, what do you think happens to the threshold voltage, VTH? If VSB is 0,
And it's equal to VT naught.
It's going to be VT naught, which is the nominal value. Okay, when somebody gives you, when VT naught is given or V3T is given, I use the term VT interchangeably with VTH, interchangeably with VTN. Earlier in the last problem, it was given to be 0.5 volts, right? So that's the nominal value, the nominal threshold value. So the threshold value is not going to change when VSB is 0. Okay, but when you increase VSB, okay, when you make the bulk more negative with respect to the source, the threshold voltage goes up. Okay, the threshold voltage goes up. So that's the idea that you want to understand. Is the rest is all you're very familiar with plugging in numbers, punching numbers into calculator, and then looking at this CF term, the gamma term, so on and so forth. Intuitive understanding is what I'm after. Okay, if you change the body potential with respect to the source, that's going to change the threshold voltage. Okay, if you tie the body and source together, this is the source, this is the body. If VSB equals to 0, then there is no change in threshold voltage. It's going to be the value that you saw earlier for that MOSFET. Okay, but if you play around with this value, if you make this guy go up and down, okay, that changes the threshold voltage, and that's the idea of body effect. Okay, body effect is body or the bulk potential modulates the threshold voltage. Okay, based on this equation here, if VSB, if the bulk is more negative with respect to the threshold, with respect to the source potential, what happens? Well, that's the idea, right? So here is the equation that you want to remember, and this is an equation that you can afford to forget if you want to, but kind of is there. If you want to make notes of it and use it as on a cheat sheet, that's fine with me. Okay, so that's the idea of V threshold voltage being modulated by the body potential. That's the idea of body effect. Okay.
So can you go through the body effect once more, like the definition, but it.
The definition of body effect is by changing the bulk potential up and down, the threshold voltage changes.
Okay.
Okay, that's all there is to the body effect. The threshold voltage goes up or down with the VSB. So far we have been, the idea of body effect is, so far we have been ignoring this terminal, this body terminal here. But body terminal cannot be ignored because it factors into the ID equation through V threshold. It changes the V threshold. Okay.
So if it changes threshold, so it changes whole operation of MOSFET, right?
It does not change the operation of MOSFET. Remember, I started out by giving you an expression for it. You were the person who told me what happens to ID as a result of change in V threshold. ID is mu n, C oxide, W over L, VGS minus VTH, the whole squared. Remember, I asked you a question. What happens if VTH goes down? You were correctly mentioning that ID goes down, correct? That's the idea you have to understand. Therefore, the body potential has an overall effect on ID. Okay, changing the body potential changes the drain current. Make sense? So it does not change the overall operation of the MOSFET. It just increases or decreases ID. Correct? Manveer, right?
Yes. Yes,
Yes, you
Professor.
told me that ID is going to change as a result of VTH.
Yes.
Okay. Therefore, body potential modulates VTH and therefore ID. Okay. That's the idea of body effect. Other questions, please.
What is phi and gamma?
Phi and gamma, right? Gamma is the body effect parameter. Okay. Pretty similar to GM. It's we'll talk about gamma later when we talk about GMB VBS. Okay.
Is
The
it
idea is
a measured quantity? Sorry.
it's a positive constant. Phi as well. Phi is also the work function. Okay, so these are parameters of the underlying semiconductor physics for the MOSFET.
Is it based on the IC or is it based on just the material?
It's based on the technology that we use. It's based on the IC technology that we use.
Okay.
Okay, and it really depends on the doping concentration. Okay, gamma is a function of the oxide capacitance per unit area, the doping level in the substrate, which is the bulk, which is the body, and the epsilon of silicon. Okay, so it's an underlying physics phenomenon. It really depends on the doping level concentration of the substrate and the epsilon permittivity of silicon, so on and so forth. This guy, phi f, depends on, so you can think of it as an artifact of the underlying physics, the substrate doping level to the intrinsic doping level. Okay, KT over Q. Okay, so these are terms that characterize the underlying process technology depending on Ni and N sub values. Okay, so that's a good question that you pay attention to these details. Along with that, the big picture that I want you to gain is the threshold voltage changes as a function of VSB. The rest is all constant. Okay, gamma is a constant for a given technology, phi f is a constant, and VT naught is also a constant. Okay, nominal value. So the only variables here are VSB and VTH, and they are related using this equation here. Okay. Other questions, please. Okay, there is a reason. If you want to look at this in more detail, we'll talk about this in 151, 234 course in your upcoming classes. Okay, where it's a required course for you, and we'll deal with this in a bit more detail. Okay. Similarly, we'll also talk about the higher order effects as well. Okay, there are a lot of higher order effects. As a matter of fact, what I like to do, and this is, I like to save the best for the best explanation for these higher order effects for 151. What I typically do before we were going online, when we had this in-person classes in good old days, okay, I would actually do a demonstration in the class where students become the electrons of a MOSFET and then the source and drain terminals. So I do a demonstration with you students um, modeling a MOSFET, organic MOSFET, okay, a human MOSFET, and then explain all of these terms in very, very intuitive terms, not getting lost with the equation, not getting lost in the equation. Okay, so there are a few higher order effects that I really want to talk about, quickly talk about without spending a lot of time. There are leakage currents. Okay, pay attention to the fact. Questions, please. Other questions so far? Okay, if at any point in time you feel that I'm going too slow or too fast, you can stop me and then ask me to change. Okay. I want to talk about leakage currents here. So we looked at two higher order effects. We looked at channel length modulation, and we also looked at body effect. Body effect simply means it acts as a backgate. The body acts as a backgate, and it modulates the threshold voltage. And as a result of the change in the threshold voltage, ID changes. Okay, by changing the bulk potential, the drain current changes. That's the idea of body effect. So we looked at channel length modulation, and we looked at body effect. Okay, now we are talking about leakage currents. Okay, leakage currents are happening mainly in three terminals. Okay, the reverse bias current, the small teeny tiny amount of current flowing through this diode from, remember, the only current that I want in a MOSFET is from drain to source, ID, N-channel MOSFET, right? This is, the arrow is shown like so, outward from source, okay? I want the drain, that's the current that I want. I only want the current flowing between the drain and source, okay? But in addition to that, there may be some kind of leakage currents that we want to pay attention to, okay? The reverse bias PM junction here, that could be a problem. That's one leakage current. And the reverse bias current coming from the drain to the substrate, that's another source of leakage current. Okay, two sources of leakage currents. In addition to these two sources, okay, there could be a very, very bad source for leakage current through gate. Okay, this guy. What is the current that should ideally be going into the gate? What should be the current going into the gate?
0.
0, thank you. Because remember, all of this guy was an oxide, it's an insulator, okay? It's fundamentally voltage charges that are separated. There's no current going in through this oxide. Okay, that's the purpose of oxide right there, to act as an insulator. But at really, really small dimensions, when you're using really small voltages, really small T oxide, this was the T oxide, right? The thickness of the oxide. Okay, when you're using a really small oxide thickness, some leakage current happens through the gate. So gate is not essentially 0. There is some leakage current, which is really, really bad in push technologies at a nanometer range. Okay, so that's at 10 nanometers, at 3 nanometers, which is really in the making. Okay, some of these really pushed technologies at um, a few nanometers range, the oxide that is supposed to be an insulator does not provide a perfect insulation. There is some leakage current that leads to a problem. Okay, so there are three sources of leakage here that we looked at. There is a reverse bias current from the source to the substrate. There is a reverse diode current. Okay, this diode current, when we reverse bias this, even then there is a small amount of current, IS, reverse biased current in the diode. Okay, that's a leakage current. The same on the right hand side as well. And in addition to that, the amount of leakage current going through the gate. Okay, that's a problem. That's a leakage. That's a higher order effect. Okay, for technologies with channel length less than 130 nanometer, there is also there's also the idea of uh, leakage. And in addition to this, there is also a subthreshold leakage. Remember I mentioned subthreshold leakage, that is in between off and on regions. There is a sub-threshold region. Okay, it's also called leakage region. That current where the MOSFET is supposed to be off, there is still some leakage current anyways, that contributes as well. Okay, that's a problem as well. Okay, that's a higher order effect, and we'll talk about this in 234 at more depth. Okay, there is Dibble effect, drain induced barrier lowering. So V threshold goes down at short channel length. Okay, at shorter channel length, V threshold goes down as a function of the drain voltage. Okay, that's a higher order effect that creates a a non-ideality for us. In addition to that, so all we are doing is we are looking at this equation. Let's see, ID, and this is something we'll come back to looking at over and over again. ID is 1/2 mu n C oxide W over L VGS minus VTH the whole square. If you want, you can even incorporate 1 plus lambda VDS. Okay, so far I mentioned that ID is dependent on the terminal voltages VGS, VDS, right? So far we saw only these guys, VGS and VDS, as variables. I pretty much assume that mobility is constant, the V threshold is a constant, and then we came back and we revisited this observation and mentioned that, well, VTH is not a constant, it's a variable that depends on VSB. Okay, that's the body effect. Let's see, V threshold is a function of VSB, is the idea of body effect. Okay, V threshold is a function of the drain voltage. That's an idea of drain induced barrier lowering. Okay, here is another dependence. Mobility that we assumed constant, this guy that we assume to be constant, is not quite constant. Okay, that changes as well. Mobility degrades. Okay, mobility degrades and velocity saturation occurs. So mobility changes as a function of VDS. Okay, this is the idea of velocity saturation. Mobility changes as a function of VGS. That's the idea for mobility degradation. Okay,
Professor, like mobility is like movement.
mobility is the dependence of the speed of electrons, charge
Speed.
carriers. You see,
Okay.
yeah, the velocity of electrons in semiconductor, how mobile they are, how quickly they can move, get from point A to point B. Does that make sense?
Yes.
So don't get lost in the nomenclature or the verbiage here. This is really verbose slide. All you want to understand is when you're looking at this equation, ID is 1/2 mu n C oxide W over L VGS minus VTH the whole squared into 1 plus lambda VDS. Okay, so far we assumed that VTH was constant, but that's not really the case. VTH has some dependence on VSB, and it also has some dependence on VDS. That is captured using body effect, and that's also captured using Dibble effect. Then we look at the dependence of mobility. Let's see the dependence of mobility mu n. Okay, as it turns out, mobility depends on the VDS value and VGS value. So mobility is not constant, but it is a function of VDS, and it's also some function of VGS. Okay, so that's the idea of velocity saturation, and you can think about this as if you think about raindrops, okay, falling from clouds up in the sky. They can only accelerate to certain velocity, and once they reach terminal velocity, they don't gain any more speed. Their velocity is constant, right? You know the idea of terminal velocity, okay? When a body is falling from sky, when some object is falling from sky, especially something light is falling from sky, it can only accelerate so much. Its velocity can only accelerate, it can only increase so much as a result of gravity. After some time, what happens is the acceleration acting, pulling it downwards, is counteracted by the air resistance, okay? And it keeps from gaining further speed. That's where the velocity saturates for that raindrop, okay? It reaches terminal velocity, okay? It reaches a constant high velocity, and the velocity does not go up, even though there's uh, acceleration due to gravity acting on it. The force of air resistance counteracts that. Okay, so that's the idea of velocity saturation that is happening because of um, lateral electric field, VDS, affects the mobility. Similarly, VGS affects mobility as well. And that's the idea of mobility degradation. Mobility drops at higher VGS values. And that's the idea of mobility degradation. Okay, and then breakdown happens when the PN junctions break down at high reverse bias voltages. Okay, this has to do with the reverse bias PN junctions that I mentioned here. In the PN junction here, when they break down because of high reverse bias voltage, there's a large amount of current flowing in the wrong direction. Okay, that's the idea of breakdown. And punch through happens if the depletion regions surrounding the drain and source touch at VDS, at really large ID can happen. Okay, let me spend a minute of time there. I don't want to take up a lot of your time here. Okay, this happens in really pushed technologies. Okay, when the distance between source and drain is really small. Okay, when the at really small dimensions, okay, at really small um, device dimensions, when the length is really small and you apply a large positive voltage on the drain, okay, like I mentioned earlier, the effect of drain reaches further and further, closer and closer to the source. And at some time, the drain actually overlaps the source, or the effect of drain actually overlaps the source, and that leads to a large amount of current. Okay, that's the idea of punch through. Okay, this happens in really small transistors in the order of um, 65 nanometer, 45 nanometer and less. Okay, when the length of the MOSFET is less than few nanometers, what happens is the drain induced, not the drain induced, punch through happens. The drain value, the effect of drain gets so close to the source that it practically sits right on top of the source. And that leads to what is known as a punch through. Okay, so that's the idea of punch through. And then there's also temperature effects. As the temperature increases, both VT and mobility increase. As mobility increases, mobility decreases, okay, and the threshold voltage increases, okay. So these are all called higher order effects, okay. We looked at the drain current equation. ID is 1/2 mu n C oxide W over L VGS minus VTH the whole squared into 1 plus lambda VDS. Okay, The higher order effects simply change the mobility as a result of, as a function of VGS and as a function of VDS. They also change V threshold as a function of VDS and as a function of VSB. Then mobility is also changing as a function of the temperature. Okay, V threshold is also changing as a function of temperature. And that's all there is to these higher order effects. Okay, higher order effects simply mean that they affect the voltages VDS, VGS. These have effects that are not obvious to us in the first glance. They change the terms that we thought were constant. Okay, that's the idea of higher order effects. Questions, please. What questions do you have at this time? I know you are curious about the exact operation of these, and what I want you to do is to hold on to that curiosity. We'll deal with this in 151, the exact underlying physics that changes the mobility as a function of temperature, as a function of the vertical field, which is VGS, and as a function of the lateral field, which is VDS. Okay. So for now, the idea of higher order effects is that VTH and mobility are changed as a result of the terminal voltages. Okay? Questions, please. Okay. So these are the higher order effects. So let's look at DC biasing of MOSFET. There are a couple of problems that I really want to do. So this is very similar to PN junction diode biasing. MOSFET need to be biased on, and typically we like to bias it in saturation region for amplification. Okay, DC voltage, that's the idea. All of these concepts, the DC coupling and the idea of biasing in MOSFET in saturation region, they become much more obvious when we look at the problems. Okay, so let's look at the problems, and this is the concept that I was waiting. I was in a hurry to get to the problems, just so all of these concepts become much more obvious. Okay, so let's look at the problem that is about biasing. Okay, it's about biasing simply means applying proper terminal voltages to put the MOSFET in on, and then in linear or saturation, mostly saturation for amplification purposes. Okay, so that's the idea of biasing. Biasing means applying proper terminal voltages to ensure saturation region of operation, mostly saturation. Okay, so let's look at this problem. Okay, this is a design problem. Okay, there's a difference between design and analysis. What's the difference between design and analysis?
In design, you have to design the circuit from the scratch, and analysis, like you are provided the circuit and you need to solve it. Maybe.
In analysis, right? In design, you're given specifications. Okay, I want the power supply. I want the power supplies to be so much, the power consumption to be so much, the voltage at this node to be so much. VD spec, power consumption spec, ID spec. The specifications are given, and you are expected to come up with the values for the different design parameters. Okay, you are expected to find a suitable resistance. Okay, think of design as creating a circuit, okay, to meet certain specifications. Analysis, on the other hand, is you don't have any choice in terms of picking devices or picking all of these components. They're all set, okay? RD value, so this is given. You're expected to find out the design parameters. On the analysis side, the other hand, the RD, W over L, all of these RS, all of these components, they are given. Okay, you only have to find out what the terminal voltage is, what what the gate voltage is, and what the drain current is. Okay, so in terms of design, design is creating a circuit to meet some specifications. Analysis, on the other hand, is to look at a circuit and derive the different terminal voltages. Okay, so let's see that play out in here. The first problem that we are going to look at is a design problem. So let's see, we are expected to design this circuit in 521, meaning what's the value of RT, what's the value of RS. RD is to be found out, RS is to be found out. What is given? Okay, given is ID, remember? Okay, ID is given to be 0.4 milliamperes. Okay, VD, this guy, the terminal voltages are all given. This guy is given to be 0.5 volts. Okay, what else is given? The threshold voltage, V threshold, is given to be 0.7 volts. Okay, and mu and C oxide is given to be 100 microamperes per volt squared. Length is given to be 1 micrometer. The width is given to be 32 micrometer. And an important consideration, the channel length modulation is given to be 0. Okay, now what we have to find out is the value for RT and RS. Let's see if we can do that. I'm going to copy this. Is everybody with me so far? Copy this. Let's see if I can add a page here. Okay, this is a design problem, problem number 5.3, right? Problem. It's a design problem. Meaning that we would have to pick values for the components that meet some specs. Okay, specs are given. Okay, the specs that are given are this guy. Okay, ID is given to be this value. And what's the circuit, by the way? The circuit is there's the drain over here. There's the source. The gate is tied to ground. This guy is tied to power supply, which is 2.5 volts. VDD is given to be 2.5 volts. There's a resistance RS over here. RD is this guy. This guy is tied to the negative power supply. Negative 2.5 volts. Yes, VSS. Negative 2.5 volts. Okay, so how would you go about solving this problem? How would you go about solving this problem? Let's see. Let me, what is given? The voltage here, VD, remember, is given to be 0.5 volts. Okay, the voltage down below, okay, let me pick this guy. The VS, is VS given at all? VS is not given, but we are expected to find the value for RD and find the value for RS. Okay, notice that ID is given. Okay, ID is given to be 0.4 milliamperes. Okay, once I have ID and I have a value for VD, I should be able to calculate RD, right? VDD minus VD over RD equals to the drain current. The potential drop across this resistance should give me ID, the potential drop over the resistance value. Right, everybody with me so far?
Yes.
So when you plug that in, VD is given to be 0.5 volts. So this guy is 0.5 volts. This guy is 2.5 volts. Okay, ID is 0.4 milliamperes. When you plug that in, you get a value for VRD to be, let's see. So all of these are known. VD is known, VDD is known, ID is known. So it's just a matter of finding out RD. Okay, RD will come out to be 5 kilo ohms. Okay, so that's the first part of the problem that we were out to solve. Okay, that's the easy part, finding RD. All right, finding RD is the easy part. So the first problem is to find the value for RD. RD came out to be 5 kilo ohms. Okay, we got the value for RD. How would you find RS? Okay, that's the second design parameter that we want to do, right? How would you find RS? Think about it.
Maybe we need to find VS first.
We need to find Vs first, sure. The reason is, if this guy is Vs, let's say, if this guy is Vs, okay, the voltage there is Vs, okay, Vs minus VSS, so the voltage at Vs minus the voltage at the other end of the terminal by Rs will give you what? Will give you the current flowing through here, right?
Yes.
Which is the same as ID, remember? There's no current flowing in this direction because that's the gate. So all the current coming in this branch has to go through the branch down below. So we already know ID, right? So we have a value for ID, okay? So we have the value for VSS. We have the value for ID. If we find out the value for VS, then we are good to go. We can find out the value for RS, right? So the only unknown in calculating RS, so let me rearrange here. RS equals to VS minus VSS by ID. Okay, we have all except VS. So Manveer, you're right. But how then would you find VS? Okay, that's the unknown now. How would you find VS? What region of operation is this MOSFET in? What is the region of operation for MOSFET, for this MOSFET? Is it on? Obviously it's on because there is some drain current, right? So it's on. Is it in linear region or is it in saturation region?
You don't know that yet.
But do we have all the information to find that out?
So ground is grounded, right?
The G is grounded. So G is grounded. So this guy, the gate, is at 0 volts.
Okay.
But we definitely have all the information to find out if this MOSFET is in linear or saturation region. What's the condition for us to verify the region of operation? What condition do I have to check for?
Like
We should compare VDS with VGS minus VT.
minus VTH.
VGS minus VTH, right? So it appears that S is not available, but that's not a problem because this is what I'm going to do. I'm going to write VDS as VD minus VS, right? And then I have to compare that VGS minus VTH, which is VG minus VS minus VTH. So this guy is VGS, this guy is VDS, right? So what I'm going to do is, because I don't know VS, I don't have to panic. I can get rid of both of these on both sides of the equation. Okay, I can subtract both of these on both sides of the equation. So it's like saying, if I'm comparing 5 and 9, that's exactly same as comparing 5 minus 2 and 9 minus 2. The inequality is not going to change by subtracting a same value on both sides. Okay. Similarly, if 6 and 6, when I'm comparing them and I add the same number on both sides of the comparison, the relationship is not going to change. By the same argument, if I eliminate Vs from both sides of the argument, the relationship is still going to be the same. So VDS, when you're comparing it with VGS minus VTH, it's the same as comparing VD with VG minus VTH. Okay, let's compare VD to VG minus VTH. Okay, what's the value for VD? VD is 0.5 volts.
0.5 volts.
Value of VG,
0.
VTH,
VTH is 0.7, 0.5.
0.7. Yeah, you're right. VTH is 0.7 volts. Correct. My bad. Okay, so VD is definitely greater than VG minus VTH. So what region of operation is this in?
Saturation.
It's in saturation region, right? So VDS is greater than VGS minus VTH. That's in saturation region of operation. Is everybody with me? So all I did was to find the region of operation. Now, once I have the region of operation known, I can use this equation. ID is 1/2 mu n C oxide W over L VGS minus VTH the whole squared into 1 plus lambda VDS. Correct? Once I know I'm in saturation region, I should be able to use this equation. Is everybody with me so far? Yes or no?
Yes, we are.
So how can we simplify this equation? Get rid of terms that I don't need.
We can remove the very last part because lambda is equal to 0.
Lambda is given to be 0, so I can get rid of this guy. I'm going to write ID is 1/2 mu n C oxide W over L VGS minus VTH the whole squared. But what would I use this for?
To find VGS.
Why do I need to find VGS? So VG minus VS minus VTH the whole squared. Okay, it seems W over L mu n C oxide 1/2. So I'm writing it forwards and backwards. So there's no excuse for you to forget this equation here. Okay. Now, it seems the whole purpose of trying to find the region of operation and applying this equation is to find VS, right? Because we were stuck here. That's the only unknown. VS is the only unknown for us. If we know VS, we should be able to calculate RS. We should make progress, right? That's the idea of RS, design problem. In order to do that, I have just about everything, okay? If you think about it, the mu and C oxide value is given. W over L value is given. VG, this guy is tied to ground. VTH is tied to, is 0.7. Oops. ID is given to be 0.4. So we have just about everything we need to calculate VS. Once we calculate the value of Vs, I should be able to use the equation value and plug it back in here to get the value for Rs. Does that make sense? So to recap, what I have done was finding the RT is really easy. It's just the Ohm's law. I have this voltage and this voltage, and then divide that by the current, I get the resistance there. Finding Rs is also application of Ohm's law, except that I don't have the voltage here. That's unknown. So it's in order to find this Vs that I go on this wild goose chase of trying to find the region of operation. Once I know the region of operation, I'm going to use this equation and plug in all the knowns to find out Vs. Now I come back to plugging in the value of Vs into this equation to find value. Does that make sense? Okay, so what I'm going to do is to clean this up a touch. No, like so. I'm going to bring all of that down like here. Okay, it's in saturation region of operation, and then we are able to find Vs. Okay, so I don't know, the Vs value I think was found to be negative 1.2 volts. This guy comes out to be negative 1.2 volts. Okay, even as I'm plugging the numbers in here, you can verify that this gate is at 0 volts and the source is at negative 1.2 volts. So the gate is above the source by more than a threshold voltage. So this is indeed on. Okay, once this is on, it is in saturation because the drain is at a higher potential than the gate. The drain is at a higher potential than the gate, so it's in saturation. So once this voltage is 1.2 volts, I should be able to calculate the value for Rs. Rs was calculated to be 3.25 kilo ohms. Does that make sense? Okay, so that's the approach that we followed here, the design problem, to find the value of the devices that meet these specifications. Okay. All right, let's do another problem. This time we'll do an analysis problem where all the node voltages are given. We are probably expected to find the all the device characteristics are given. All the devices, the elements, the resistance values are given. We are expected to find the drain currents, drain voltages, so on and so forth. Okay, so in a design problem, we were given the terminal voltages and we were asked to find the values for the resistances. Okay, let's see the next problem we have here. Okay, is it so? Plug that numbers in, and I don't want to get into this 1/2 132 VOV squared. Just plug that in and into the calculator. See what we have here. The next problem, example 5.6, is an analysis problem. In the analysis problem, the values for these resistances are given, known. Okay, now you are expected to determine all the node voltages and currents through all the branches. Okay, what's the current in this branch? What's the voltage over there? So on and so forth. Okay, that's what we are expected to find. We don't have to pick values for RD. Okay, let's see if we can solve this problem by, okay, let me see if I can copy this. If it does, let me copy here. Okay, analysis problem. What is given here? Given is that VTN is given to be 1 volt. Mu n C oxide W over L is given to be 1 milliamperes per volt squared. Okay, channel length modulation can be neglected. Okay, and then the resistance values are given. Analysis problem. Let's try to solve this problem, analysis problem. Okay, add a page. Let me see if it lets me paste image. There you go. Okay, this is problem number 5.6, analysis. Okay, all of these terms are given. Copy that and paste it over here. Okay, VTH value is given, mu and C oxide is given, and then lambda is given. Okay, we are expected to find, okay, we are expected to find the drain voltage VD, okay, the source voltage Vs, the gate voltage VG. Earlier in the problem that was given to be ground, right? Here we are trying to find VG value. That's good news, isn't it? Dr. Fauci says there's no need for a second lockdown. We are also expected to find ID, which is exactly the same current that's flowing in here as well. And we don't even have to mention that the current going into the gate is 0. Okay, so this drain current is unknown. Okay, questions please. Questions so far. So look at this problem and tell me if there's a voltage or current or some quantity from the unknowns that's absolutely easy to find out. What's the easiest to find out between ID, VD, VS, and VG?
I think we could find VG easier than
You can
that.
find VG easier because it's simply this potential and there's a voltage division between 2 equal resistances. So we don't even have to do any math. This voltage 10 volts is divided equally between 2 equal resistances. So we know for a fact that VG is going to be 1/2 of VDD. Check. First problem solved. Now what? What do we do now? So there are unknowns here. There is VG is not an unknown anymore. We found its value to be 5 volts. Okay, so I'm going to put it as a known value. So we'll leave it there. Okay, VG is found to be 5 volts. Now ID, VD, VS are the values that we want to find. VG is known to be 5 volts. So now why don't you pull a trick out of your hat and tell me how you want to proceed from here. Don't forget to make use of the information that's already given to you, VTH, mu and C oxide, lambda equals to 0. So all of that information is given to you. What can you do with that information in order to find ID, VDS, VD, and VS? Is there an equation at all that relates all of these terms? Do we know an equation that incorporates all of these? ID, VD, VS, VG, V threshold, UNC oxide, lambda.
The drain current equation.
The equation we are using for ID is equal to
The
half.
drain current equation, okay? So if you talk about drain current equation, I have a doubt here. There are two equations. ID is 1/2 mu n C oxide W over L VGS minus VTH the whole squared. And I can ignore 1 plus lambda VDS term. This is if the current is in saturation. ID is mu n C oxide W over L VGS minus VTH into VDS minus 1/2 VDS squared. This is in linear. So how would I go about? Which current would I pick? Which equation would I pick?
I think we have to make an assumption.
Yes, exactly. So I'm going to assume, I'm assuming that the MOSFET is in saturation. I'm going to make an assumption that the MOSFET is in saturation and use this current expression. ID is going to, and then eventually I'll verify if my assumption is correct or not. Okay, I'll verify if my assumption is correct or not. So in order to do that, ID is 1/2 mu n C oxide is given W over L, all of this term, right? Mu and C oxide W over L is given to be 1 milliampere per volt square. So I'm going to plug in a value for this guy, okay? 1 milliampere per volt square times VGS. So this is VGS, right? VGS minus VTH, the whole squared, okay? So this is ID is 1/2 1 milliampere per volt squared. VG, I just found that value to be 5. I don't know VS. VGS is VG minus VS. Minus VTH is 0. What's the value given for VTH? 1 volt, right? VTH was given to be 1 volt. So I'm going to use that. I'm going to use a value of VTH to be 1 volt over here, the whole squared. So it seems ID is 1/2 into 1 milliampere per volt squared to 4 minus Vs, the whole squared. Geez, there are still two unknowns, okay? And I have only one equation here. So it seems in order to solve for two unknowns, I would need two equations. Okay, the first equation is this guy. The second equation is going to come from here. Okay, the second equation is going to come from here, noting that Vs minus 0 over 6 kilo ohms is going to give me ID. So that could be my second equation. If I use my second equation here, this guy, okay, then ID equals to Vs minus 0 over 6 kilo ohms. Right? That's coming from the fact that the drain current flowing in here is the voltage dropped across the resistance Rs, which is Vs minus 0 over the value of Rs, 6 kilo ohms. Okay, now what do we have? We have two equations, two unknowns. Okay, this guy is, I'm going to simply say, two equations and two unknowns. Now we can solve for this equation. Okay, now we can solve for we get a quadratic. Okay, we get a quadratic. If we plug the value of Vs to be ID times 6 kilo ohms, okay, in place of Vs. Okay, so if I'm going to use equation number 2 and plug that into equation number 1, I get a quadratic in ID 36 ID squared times 10 to the 6 minus 50 into 1000 times ID plus 16 equals to 0. Okay, so it turns out that these two equations, the quadratic equation results in this, and ID is going to come out to be two values, 0.89 milliamperes, or ID is going to be 0.5 milliamperes. Okay, two values emerge for ID from this equation, from the quadratic equation, solving equations 1 and 2. So one of them is going to be correct and the other is not going to be valid. Okay, ID can be 0.89 milliamperes or ID can be 0.5 milliamperes. Okay, then how would you know which of these values is correct? So plug that value 0.89 into ID and see the value for VD. That comes out to be 7 volts. If you're using a value of ID equals to 0.89 milliamperes, then VD comes out to be 7 volts, which implies that it is over the gate voltage. It is, let's say, VD is equal to 7 volts, Vs is equals to 3 volts. Okay, this seems to be proper for the operation in saturation region. Compare that to the other case where ID is 0.5. If ID is 0.5, then VD is going to be 10 minus 3. It's going to be, let's see, when VD is, let's see, this is applicable for actually 0.5 milliamperes. If you plug in ID equals to 0.5 milliamperes, VD is going to be 7, Vs is going to be 3, and that means the MOSFET is on and it's in saturation if ID equals to 0.5 milliamperes. If you check the same condition for ID equals to 0.89 milliamperes, okay, you'll see that the MOSFET is actually not operating in, you'll get that Vs is equals to 0.89 milliamperes times 6 kilo ohms. Okay, 6 kilo ohms. That comes out, that implies Vs equals to 5.33 volts, which is above the gate voltage. Okay, that implies the MOSFET is off. That implies the MOSFET is off. If the MOSFET is off, it cannot support a current of 0.89 milliamperes. So that's obviously invalid result. The idea being, okay, the idea that this is invalid and this is validated. This validates our assumption that we are operating in the saturation region. Okay, questions please, questions so far.
Professor, like you said, there are like two equations. Can you show that equation?
You want me to show the equations? I'm going to clear all of this. Okay. I'm going to clear all of this. One equation, there are two equations, right? One equation is coming from ID equals to 1/2 mu n C oxide saturation for the MOSFET. Okay. The second independent equation is coming from this resistance here. Okay, the second independent equation is coming from ID is the voltage dropped across the resistance over the resistance value. Okay, one equation is coming from the MOSFET operation, and the other equation, saturation condition, the other equation is coming from the Ohm's law here. Okay, so if you look at those two equations, you'll see that one equation is indeed coming from the MOSFET saturation region of operation. That's this guy. And the other is coming from Ohm's law, which is that guy. Does that make sense? Two equations, two unknowns, you can solve them.
Like there were two more equations that you used in the starting of this problem, I guess.
Which equations did I use?
Like you said, there are like two equations for the drain current.
Oh, yeah. There are two equations for the drain current. Are you talking about this guy? ID is
Yes.
mu
Yes.
C oxide W over L VGS minus VTH into VDS minus 1/2 VDS squared in the linear region. There are two equations.
So this is for the linear, okay.
This is for the linear region. So what I'm going to do is I'm going to assume that the MOSFET is in saturation. So I'm not going to use the linear equation. I'm going to use the current that corresponds to saturation because I'm assuming the MOSFET is in saturation. Okay? Other questions, please. Okay, so in spite of my best efforts, I am unable to cover the topic on MOSFET amplifiers. Let me quickly give you, I hate to leave, all I will tell you is MOSFET amplifier simply is GM R0 in parallel with RD. Negative of that will give you the gain. Okay, what I mean is if you have a MOSFET that looks like this, okay, there is a resistance in the drain RD, VDD, okay, and this guy is connected to ground, and this guy is connected to VG, a signal source, okay. The gain of this amplifier is GM. GM is, I gave you the expression for GM earlier, okay. GM is simply the derivative, partial derivative of drain current with respect to the gate to source voltage. Okay, and you will come back to look at this over and over and over again. The voltage gain is if you have a resistance RT and R0 is the effect of channel length modulation, which you simply calculate by 1 over lambda ID. R0 is the same as RDS. It's calculated as 1 over lambda ID. Okay, the gain of a MOSFET is simply negative GM. This is the transconductance, okay, which is this value. The transconductance times R0 in parallel with RD. That's the problem that you're going to solve here. Okay, you are expected to find the MOSFET amplifier gain. Okay, what's the you're applying a signal. What's the gain of this MOSFET when there's a resistance in the drain? Okay, you will when you solve this problem using the small signal model, sure enough, you'll see that the gain is negative GM R0 in parallel with RD. Okay, so that's the application of that is the problem here. Okay, you're expected to find the value of AV. So in order to do that, you would use ID. And once you have ID, you should be able to calculate GM. Okay. Once you calculate GM, you should be able to calculate RDS from the lambda value. Lambda is given. Okay, lambda times ID will give you GDS. 1 over lambda ID will give you RDS. So RDS in parallel with RD times negative GM. That will give you the gain of the MOSFET. Okay, I tried my best, but in the time that we have, okay, there's a little bit of gap, and fortunately Dr. Heagley's videos are available to you. And I just want to remind you again that my lectures are only meant as an addendum, as an additional resource, not as the main teaching resource. So I hope you are able to go through Dr. Heagley's videos to find out about the small signal MOSFET models. Regardless, it's simply negative GM primes are not in parallel with RT. Okay, questions please. What questions do you have at this time? All right, we'll stop here, and then I'll come back around 12 o'clock, 12:10. It may be a little bit after 12 for me to finish lunch and join you. Okay, so you keep working on lab number 6, the MOSFETs, an interesting lab. Okay, I'll be in and out today, so for during the lab. So Kyatiha, the TA, will be doing most of the demonstrations for you. Okay.